Okay, now that we understand different phase composition, subcooled liquid, superheated vapor, mixture, and supercritical liquid and vapor, let's go ahead and see how we evaluate properties of a state. So we will start with the simplest possible situation. Let's say it's given to us that we want to evaluate all the properties for a state called state 1, and let's say pressure is 100 kPa and it's saturated liquid. So the first step, so we'll outline how to find properties of any saturated state, saturated liquid or vapor. So if we do a TS diagram, we immediately know, draw the dough and draw a constant pressure lines, and because the pressure is given to us 100 kPa, so let's say this is 100 kPa line. So where is my state? The first thing is to locate the state that you want to find. It's saturated liquid. So as you can see, this is basically the F point here. So it so happens that the phase change model is so complicated that we don't have simple formula. So we cannot really find enthalpy, entropy, etc. from simple formulas. So these properties are all tabulated. So let's go and see how a PC table looks like. So we go to the table modules, or in the back of your book, you'll find in appendices this tables. So here is the PC model. As you can see, this entire row is all about PC model tables. And you can see that once you know the materials, of course we are talking about steam in this particular problem, H2O. So H2O tables are sometimes called the steam tables. Okay, so let's begin. Of course, the same thing can be done for any other fluids here. There are almost about 7 different PC model fluids. So let's see how we go about finding the properties of a saturated liquid. So there are two saturation tables. Table B1 is called PSat and table B2 is called TSat. These are basically the same table, except in PSat, the pressure P becomes the independent variable. So as you can see, the first column is pressure. So at a given pressure, you can immediately figure out the saturation temperature, the second column. So if a pressure is given, you can find the saturation temperature. Remember what that is, like a boiling temperature. So if the pressure is 100 kPa, we already know the answer, which is 0.1 MPa. Notice that the unit of pressure switches here, and the temperature is almost 100 degrees Celsius, as you can see. By the way, the temperatures here are all in Celsius. And notice after that, after the temperature column, there is VF, VG, UF, UG, etc. That means the F properties are listed explicitly and G properties. So if I have a saturated liquid, I know that my answer will be all F properties. So at 100 kPa, which is obviously, this is my pressure, 0.1 MPa is 100 kPa. So what will be the specific volume? This is my answer. What is U? What is H? What is S? Simple. Notice that if the pressure was not 100 kPa, suppose we are given a pressure of 130 kPa, which will be somewhere in between these two pressures. In that case, we have to sort of interpolate between values. So to find the value, say, between this and this, we have to find some number in between. Instead of spending a lot of time trying to interpolate, what we should be doing in that case is just kind of guess what will be a reasonable number in between. And you'll get good at it, and believe it or not, you will gain sufficient accuracy just by I estimate, then spending a lot of time trying to interpolate manually. Okay, so finding the properties of this state is not tough at all. So answer is that look it up from the saturation table. Suppose we have another state. Let's say we want to find a state at 2, temperature is 200 degrees Celsius, and it's saturated vapor. So what you do, 200 degrees Celsius, so basically we know the temperature, let's say here, right, at 100 kPa saturation temperature was 100 degrees Celsius or 99. Okay, that's fine. So where is my state now? we know that given is 200 degrees Celsius, so it must be anywhere on this dotted line. But we know it's saturated vapor, so that must be the G point. So that must be state 2. So it's very important to locate exactly where your state is, not exactly, but approximately where your state is, and it gets much easier to find properties. As we solve many examples in the next module, you'll see that this would be very valuable, spotting your state on a TS diagram. So let's go and quickly find all the properties at temperature 200 degrees Celsius for saturated vapor. We go back to the table, but this time, because temperature is given, why use the pressure saturation? Use the temperature saturation table. And you can see, you can go there. Everything is similar except temperature is the first column. So you go to the 200 degrees Celsius. And there you have it. Now you can pick up the entire, this is our 200 degrees Celsius, as you can see. And FG, we want G, so this will be the G values. If you go up, you'll see that these are the G column. So if the question is find the enthalpy of the saturated vapor, then this will be the answer. Again, if it is in between temperature, suppose 202 degree, interpolating between the two is not that difficult. 2793 and 2796. How much error can you make? You can say it says 2794, and you'll be almost as accurate. Look at the percent accuracy involved here. Okay. Now that we know how to find properties of a saturated fluid, let's see how to find properties of a mixture. So let's start with, let's say we have a mixture in equilibrium, mixture of liquid and vapor. Going back to our, suppose at a certain pressure, this weight is putting a lot of pressure here. I'm creating a lot of pressure inside. And let's say we have this liquid vapor mixture. So we have some vapor and some liquid at a given pressure. So first, let's introduce a new property called the quality. What is quality? This is another property just for a mixture. It becomes very important. The quality is defined as the mass of vapor by total mass in a mixture. In other words, vapor is considered high quality steam. Obviously, you have to spend money to convert liquid to vapor. So this comes from the industry language. That's why it's called the quality. It's sometimes expressed in percent, sometimes by a fraction, but you understand it simply means how much vapor is there in a mixture. So X equals 1 means what? Means it's saturated vapor because it's all vapor. And what is X equals 0? Means it's saturated liquid. So that's, once you understand the quality, we can very easily evaluate properties of the mixture. Why? Because if you think about it, what is this mixture? The mixture is made of, mixture means what? Mixture means F, liquid at F state plus vapor at G state. See, that makes sense to you. Because in a TS diagram, if you draw the TS diagram and somebody says we have a mixture at a certain pressure, suppose the pressure equals 500 kPa, and we have a mixture, means what? We have some fluid at F state, some fluid at G state. That's what mixture is. So we can use the saturation table to find out mixture properties, because what is mixture after all? It's a combination of F and G states. So we need to come up with a formula that how can you extract the property, suppose my state is somewhere here, by combining F and G states. We have to somehow average the properties of F and G state. And X plays a role there. So let's quickly develop a formula. Suppose, let's say we want to find entropy of a mixture. I'm just picking entropy as an example, but it could be internal energy, it could be specific volume, all these properties. So let's say we want to find entropy of the mixture. So obviously, then it will be entropy of the F state plus entropy of the G the fluid which are in saturated liquid and saturated vapor. See if you agree with that. Entropy is sum of properties. So this is all the liquid and vapor. We can also write that this is the total entropy. So we can write mass of the liquid and entropy per unit mass of the liquid, saturated liquid. So we can simply express it like this. So what would be the specific entropy, which is S divided by mass, right? So as you can see, what happens here is if I divide by the mass, it becomes mf over m sf plus mg over m sg. You can also immediately see that what is this quantity? This is nothing but mass of vapor by total mass, right? The vapor is at G state. So therefore, that's nothing but X. And what is this quantity? We can write that as MF is nothing but M minus mg, because there is only vapor and liquid. There is nothing else. So this becomes 1 minus X. So therefore, the formula reduces to 1 minus X times SF plus X times Sg. So this is a very simple formula to understand. It says that if you want to find entropy of a mixture, find the entropy of the saturated liquid, entropy of the saturated vapor, and weigh them by the quality. See, if X equals 1, see if X equals, if we substitute X equals 1, then S becomes Sg. That's what we expect. If X equals 0, S becomes SF. Notice that if you agree with that. Well, even though we have done that for just S, the same logic applies for all other properties. So what will be U? U will be 1 minus X times UF plus X times UG. What will be V? You got it. So it's the same format that applies everywhere. So any property is a combination property here, and F and G properties can be obtained from the saturation table. And we will do a number of examples later involving a mixture. So if the quality is supplied, it is really easy to figure out the state properties of a mixture. So suppose it is given pressure equals 500 kPa and quality is 50%. Let's say question is find enthalpy. So what we do, we draw the 500 kPa line and we say, okay, so to find the enthalpy, we know enthalpy must be 1 minus X HF plus X times Hg. You can write it more elegantly if you say HF at 500 kPa plus X Hg at 500 kPa. And these values are all we need because X is already given. So I'm not going to solve the problem here. I'm just going to show you how to solve the problem. And later we'll solve the problem with all the numbers, all the glories of the numbers. So how do you find HF? We have already shown how to. So we can go back. And since in this case we know the pressure, we start with the pressure saturation table and go to 500 kPa, which is 0.5 MPa. So here we found our line. 0.5 MPa is right here. So HF we pick up from here and Hg we pick up from there, right? So therefore, once we know HF and Hg, it's just the average between the two if X equals 0.5. So this turns out to be very simple if you know X, but many a times X is not given to us. So let's say instead of X being given, suppose the same problem, a problem is a variation of this problem could be, say, pressure equals 500 kPa and H equals 1000 kilojoule per kg. I'm taking H again as an example. So if I know the pressure, suppose this is a 500 kPa line, an enthalpy is given. So we know the state is going to be somewhere on this line, right? This is the 500 kPa line. This is the locus of 500 kPa. I hope you understand that by now, that if the pressure is 500 kPa, which is given in this case, the state must belong somewhere on this line. There is no other option. Well, but where it is, it could be a subcooled liquid, it could be a mixture, it could be superheated vapor. In this problem, we are not told what it is. So you have to figure it out. How do you do that? Well, we already figured out at 500 kPa what is HF and what is Hg, right? We saw that HF was 500 kPa, HF was about 640 and Hg was 2748. I'm approximately writing. So we know these values, HF 640, Hg equals, 640, Hg equals 2748. Exact numbers are not important. So that means what? I have an enthalpy that is in between, bracketed by F and G. So my state must be somewhere here. So try to understand that. Suppose pressure and specific volume was given. Then again, we'll find Vf and Vg. And for the given value of V, if it is bracketed by these two values, we found it to be a mixture. So that tells us that we have a mixture in our hand. And how do you find? Suppose the question is find entropy. So what you do, now that you know H and HF and Hg, we can use this formula to find out X first. Once you find X, because as you can see, we know HF, we know Hg, and we know H. Therefore, X is the only unknown, one equation. So finding X is complete. Once you find X, now you find S from, again, the same template of a formula. Oh, sorry, not H in this case, it should be S, because we are trying to find entropy. And SF and Sg can be picked up, just like we picked up HF and Hg from the saturation, pressure saturation table. Well, now suppose let's find another state. Again, we don't know the phase composition, 500 kPa. And let's say enthalpy is given as 4,000. I'm just picking an arbitrary number here. So how do we go about finding a state like this? So if we draw a TS diagram, again, we draw the 500 kPa line, and we ask ourselves, do we have a mixture here or not? So the first step is always to figure out what is HF and Hg. Notice we already did that. Hg was about 2748. That's why I picked the same pressure. 2748. And look at the value of H given here, 4,000. So obviously, our state will be somewhere along this line, but it is probably, the pressure is here, but the enthalpy is higher, so it's somewhere here. This is where our state will be. I don't know exactly where, but it's superheated vapor. So we figured out that shows that we have a superheated vapor as the mixture composition. So how do you find properties of superheated vapor? That turns out to be very simple. Superheated vapor tables essentially list all the properties along a given pressure line. Once you take a look, it will become immediately clear. So let's go find out the superheated vapor table. Look, every substance has a superheated table and at least one saturation table. Only for water we have both pressure and temperature saturation table, but superheated table is there for everything else. Okay, so superheated table for H2O we open. It comes down here. If we scroll down, look, the way the tables are organized, a pressure is given. For a given pressure, there is one table. So each pressure has its own table essentially. So our pressure is 500 kPa, which is 0.5 MPa. So that's our table. So this is our table, right? So if pressure is 500 kPa, look, if I knew the temperature, I can read off any properties. But enthalpy is given. Enthalpy is given as 4,000 in this case, right? So we immediately recognize that the enthalpy is somewhere in between the two. So if the question is find the temperature of this superheated vapor, so you can see 4000 is somewhere in between, and I can just, instead of spending a lot of time, I'll say, you know what, it's somewhere in between. I'll just take 750 as my answer. Well, it may not be perfectly accurate, but you would be surprised that how good this guess is. As long as you don't make a mistake of picking a totally wrong value, you'll find this will get you very close to the exact answer, within the tolerance of an answer. So if the question is find entropy, again, we just pick up something in between, because we know our solution is somewhere in between. 4000 lies here. So likewise, we can find, VUHS and temperature given one of them. Now you may ask, well, if the pressure is 500 kPa or 600 kPa or 800 kPa, we can figure that out. What if the pressure is, let's say, 650 kPa? What do we do then? Well, if the pressure is 650 kPa, we recognize that it is somewhere in between these two, right? And 650 is closer to this guy than this guy. So basically, I would almost pick these values over that. But ideally, you're supposed to interpolate between the two tables and get a new table for 650 kPa, and then interpolate based on what property you know. So you could spend an hour easily to be trying to be very, very accurate. So I would say, don't go there. Just pick a value that is reasonable. So if the question is, okay, suppose somebody says the pressure is 650 kPa, and let's say temperature is 225 Celsius. So how will I pick my value? I will say 650 is close to this, and temperature is 225, and suppose the question is find entropy. Okay, find entropy. Then what we'll do, 225 is somewhere in between these two temperature. But so our answer will be somewhere in between these two values and these two values. In other words, suppose so from here we interpolate for 225 will be somewhere in between. It's like between 7 and 7.2. Suppose we call this 7.1 is our value here. And here, what is the value? 6.8 and 7.0. Suppose we say, okay, 6.9 is our value. So our answer should be, so this is for 600 kPa and this is for 800 kPa. If it is 700, then it will be average of the two. But we are closer to this guy, right? 650 is closer to this guy. So I'll say, if I say 7, then it becomes average. So I'll probably say 7.05 or something, so that I'm closer to this than that. But even if you pick 7.1, you will not go so wrong. Okay. And remember, we are going to use TestCalc to verify all these answers, so your guessing capabilities will improve as you solve more problems. Okay, now that we know how to find properties if the phase composition is superheated vapor or mixture or saturated liquid or vapor, let's see how we find the properties of subcooled liquid, which is also known as compressed liquid. So let's make up a problem. Let's say pressure equals, again, 500 kPa. And let's say this time temperature is given. Let's say temperature is 30 degrees Celsius. So if the pressure is 500 kPa, so this is our 500 kPa line, how do we figure out the phase composition? So we've tried to find first the saturation temperature, because then we can compare, because this time enthalpy is not given or entropy is not given. T set at 500 kPa is how much? So this temperature is how much? If we go to the pressure saturation table, that will tell us. So if we go to pressure saturation table at 500 kPa, we notice that, okay, it's right here, 152 degrees Celsius is the boiling temperature. So this temperature is 152 2 degrees Celsius. So at 500 kPa, if you put a pressure cooker at 500 kPa, water will be at 152 degrees Celsius boiling. But what temperature we have here? 30 degrees. So our line, suppose this is the 30 degree line. So therefore the state that is given must be somewhere here. Let's put some state number. Suppose we call this state 3, which was somewhere here if you recall, and this is state 4. Well, the plot is getting crowded. So we know from here already it's a subcooled liquid or compressed liquid. These are both terminologies that are used, compressed liquid or subcooled liquid. So we want to find properties. Let's say question is find the enthalpy of, find enthalpy. So how do you go about doing that? Okay, we are going to expand, zoom on this part of the diagram and develop a new submodel. So let me just quickly draw the zoomed up diagram here. Again, this is T and this is S, and this is the dome, and let's say this is the constant pressure line, 500 kPa line, and this is our state. Let's say this is our 30 degrees Celsius line, and this is our state. Maybe I should have drawn that in red color, then it will become a little bit easier to understand which is what. So this is my dome. Okay. So to find subcooled liquid property, a submodel called compressed liquid submodel of the PC model is used. What does that submodel say? So obviously a model means assumptions. According to this submodel, that V, U, and S, these three are function of temperature only. In other words, V, U, and S do not depend on pressure. So if this is my state 4, that means to find V, U, or S, you can find anywhere. It's a function of temperature only. So if you know the temperature, you can find it here, here, here. All these states will have the same V, U, and S. Which immediately means this point, we already know how to find properties at this point, right? From, if I know the temperature, I can go to the temperature saturation table and read these properties. So therefore, V can be found from the F at given T, U is U, sorry, this is U, UF at given T, and S is also given. If you know the temperature, it becomes so easy. So therefore, from V, U, and S, if you know that, finding enthalpy becomes very easy because from the basic definition, it is U plus PV. U is a function of temperature alone. V is also a function of temperature alone. So enthalpy can be found. So in this particular problem, all you have to do is to go to the temperature saturation table. In this particular problem, for instance, is given temperature is 30 degrees Celsius. So the H becomes UF at 30 degrees Celsius, which is, this is a pressure table. Let's go find a temperature saturation table. 30 degrees Celsius is here. So U is given here. UF is 126 about. So it's 126 plus pressure is 500 kPa. We have to find VF at 30 degrees Celsius. We go back there, 30 degrees Celsius. As you can see, VF is, this is our 30 degrees Celsius. Look, VF is almost like 1 over 1000, 0.001. So if you go, substitute 0.001, and you'll notice that the answer is barely different from U. But still, if the pressure is very high, pressure can have an impact, because if the pressure gets higher and higher, specific volume also gets larger. So this will contribute. So that's how we can find a property. If temperature was not given, suppose say entropy was given, suppose it was given it's a liquid, but entropy was given, then we can go back to this table because we know entropy is a function of temperature alone, and we can look at the SF table, the SF column. If entropy is given, it's monotonically increasing. Suppose entropy was given at 1, then we'll say, that must be somewhere in between these two. So therefore, my temperature must be between 70 and 75, let's say 72 degrees Celsius. So that's how we could locate the state if temperature is not given. Well, we have covered almost all the zones, and I must warn you that what I have done here is not a bulletproof algorithm for finding properties manually. There are situations where, for instance, suppose you don't know where the state is. It's possible to have complicated problem. Let's say I have a situation where some enthalpy is supplied, let's say 2000, and specific volume is supplied, 0.05. What do you do about that? Because now we don't know the pressure or temperature. This kind of situation requires iteration. In other words, you assume pressure is this, and then find HF and HG and see V's in between, and if it becomes a complicated mess. So you have to iterate until both conditions are satisfied. This will be a nightmare of a problem to solve manually. That's why we have computers. So when we use TestCalc, we can easily find this kind of properties. And of course, the TestCalc, as you know, can be launched to find properties, system or flow state. You choose one of them, and then click on the model, go to PC TestCalc, and you will notice that it will look very similar to the SL TestCalc that we have seen before, except now it has a quality X here. And by the way, as you move the pointer over, a particular property, the definition will appear at the bottom, like what is quality X is defined to remind you what it is. And to find a property, you just punch in the known properties, click the calculate button. But the nice thing is here that if you suppose we have a state at 100 kPa and a quality of 0.5, the nice thing here is that not only you can calculate, and you can visually see the state. If you draw a TS diagram, you can draw a constant pressure line, etc. One thing to notice is that the constant pressure lines doesn't look like what we have seen before. In other words, we always wrote the constant pressure lines like this, right, in our discussion. And in real life, you'll see that they almost collapse together. If you go with a microscope, you'll find a slight difference. Okay, so now that we have covered all the different zones, the superheated vapor, mixture, and subcooled liquid zone of finding properties, in the next module we are going to solve some problems, in other words, finding properties from different zones with more numbers. And mastering how to find properties of PC model is really important, because PC model is kind of the heart of all models that is used over and over again throughout thermodynamics.